Good evening, ladies and gentlemen. Welcome to this meeting of the Sacramento Valley Astronomical Society. Our speaker tonight is board member Awanish Mishra, who will be lecturing us about the moon, its history and its future. And Awanish has given talks before. He's an illustrious and trained scientist, and we're very much looking forward to what he has to say tonight about our lone satellite. And without further ado, Awanish, it's your show.
Thank you very much, Raj. I really appreciate that. I'd like to thank everybody for giving me this opportunity. Hopefully you can all hear me and see my screen. And if not, then please chime in. So anyways, I'm going to talk about the moon tonight. And in particular, I do a lot of talks on science, and I love astrophysics and quantum mechanics and those topics, and have been trained in some of those. But I spent a lot of years photographing the moon, staring at the moon. Even when I was a little kid in Minnesota, we did a lot of that, and had a lot of fun. But over the years, I became more and more interested in, so what's the moon made out of? It's not cheese, it's not this, it's not that. What's it all about? And of course, as some of you who are old enough would remember, I remember sitting in Minneapolis in front of a Philco Ford 17-inch black and white TV, watching Neil Armstrong land on the moon with my dad and my brother. And, even as an 8-year-old, I couldn't quite understand the feeling, but it was an emotional moment. It was incredible. So I've always been interested in what, landing on the moon, what's it all about? And, we've talked about eclipses and seasons and everything else, but I've wanted to always delve into the deeper aspects. Where did the moon come from? What is it? And that type of thing. So that's what this talk is about tonight. If it's hard for me to see the chat or things like that, but if someone has a burning question or make a glaring issue that you need to discuss, please chime in. Otherwise, I'd be happy to take any questions at the end as well. So I'm not stopping you, but I'm just asking you to be aware that it's hard for me to notice things as I'm focused on my screen here. Anyways, with that being said, we'll go ahead and get started. We're going to talk about, what is a moon? We're going to talk about our own moon, some of the fun facts associated, its properties. What are the leading theories, or what were the old theories about how the moon formed? And then I want to focus a little bit on tides, eclipses, since eclipses are a big topic these days, especially for next year, the impact of the moon on us and its future. Now, one thing that I have slides for, but I wasn't going to talk about is seasons. I think that's a topic that gets beaten to death, and a lot of people know about it. Not that you don't know about these topics, but I'm going to leave that one out. Unless there's a burning question at the end, I can always go back to it. So, what is a moon? Well, according to ChatGPT, the AI system, I asked it, it gave me an answer as I requested, as a haiku. Silent in night sky, circling earth, tides dance below, silver mirror shines. And the question was, give me a haiku about what is the moon. So artificial intelligence, Skynet, the Terminators of tomorrow, that's what they consider the moon to be. Anyways, so defining a moon. First and foremost, a moon is a celestial body that orbits another planet or a dwarf planet like Pluto, which I maintain still got a bum deal. But that's what, by definition, it is. It's often termed a natural satellite to distinguish it from things like artificial satellites, man-made satellites. Well, that's the only kind of artificial satellite there is, right? As far as we know. And so the orbit planets, dwarf planets, they're naturally there. They've been there for a long time. But how do they get there? Their formation. There's several accepted theories. There's the capture theory, where a planet's gravitational pull can capture a passing body just into its orbital sphere. There's the accretion, which is that theory that moons are formed by rings of material that are orbiting a planet. And there's one related to this that I'll mention a little bit later. There's also the planetary collision theory, where two objects impact and the result is one object and a second object is created between the collision. And so you have the larger of the two that it's orbiting around, or it's what's called the barycenter. One of them will be the moon and one of them will be the primary planet. So those are three common accepted theories of how moons are formed. Now, they come in all kinds of diverse sizes, shapes even. If you look at the Phobos and Deimos on Mars, where Phobos is actually being torn apart by the gravitational pull of Mars and or the stresses from it, tidal forces, and they have different compositions. So, and as you can see, our moon there on the far right isn't necessarily the biggest, but it is among some of the other moons that are throughout our solar system here. And, you know, a planet can have no moon. Venus and Mercury have no moons, or they can have one moon or many moons, or none at all. So there's a whole variety of things out there that we can look at. And as we get better at our technology improves, as we find exoplanets, eventually, of course, we'll start finding moons around them. So I wouldn't be surprised if in the next 5 years we found an exoplanet, if we already haven't, that has its own moon. So in our solar system, it's generally accepted that there's a traditional count of about 290 moons in our solar system. So Earth, as we know, has one. Mars, we're all familiar with. The one that always changes over time is 95 for Jupiter. Now, when I was a kid, it was like 10 or 12, maybe 15, probably less, I think around 10. So it's really grown. Saturn has 46 moons. Uranus has 27 moons. And Neptune has 14. And even the dwarf planet has 5, whereas Charon, is it Charon? Charon, its moon, the big one, is big enough where it even causes Pluto to wobble. By the way, the thing that I find really fascinating here is that Uranus was detected and found by Herschel. William Herschel, I believe, was the first planet discovered by a telescope. And at first, the data showed that something is wrong. It's affecting orbits and all of that, and maybe some of our theories on gravity are wrong at the time. But instead, what they decided to do was apply Newton's gravitational laws, and based on that, they were able to figure out where there might be a planet, and sure enough, there was. So you don't always have to toss out your theories if the data is kind of looking weird. Maybe you just don't have the ability to see everything at once. But going back to the number of moons, so there's 290 moons traditionally, and then there are small body, excuse me, over 460 of those. So these are asteroids, large ones, not the billions of little ones, and in the Kuiper Belt and trans-Newtonian objects and things like that. So according to NASA, there are about a total of 752 essentially moons in our solar system, which is a lot more than I expected. But so they're very common, at least in this solar system, and I suspect that's the case in virtually any solar system. And in our own system, just some representative relative to the size of our moon. Some of these other moons that are out there are obviously, our moon is not the biggest. Callisto, Ganymede, Titan, these are on par, if not bigger, certainly bigger in the case of Ganymede and Callisto. Io is right up there on par with the size of our moon. And Mars is Phobos and Deimos are much, much smaller. So they come again in shapes and sizes and all of that. So, and this gives you a pretty good idea of the moons that are out there. Well, anyways, enough about the rest of the solar system. Let's go back to our moon. So this is one of those high resolution images taken over a long time with many, many layers and pieces. And it's a pretty good shot of the moon. So let's talk about our moon for a bit here. The origin is from the Old English word Mona, or the Proto-Germanic word Mino. And so it goes back quite a ways. And it's been looked at by many different cultures that have given it many different names. In fact, my own middle name is after the Hindi word for the moon, which is Chandrama. And so my parents had that in mind when I was born, but it has dozens of different names. And by any other name, it's still the moon, as far as we're concerned. In a scientific context, it's often referred to as Luna to differentiate it from the generic term moon. And so, again, it's been around for a long time. We've looked at it, we've worshipped it, and been guided by it, not simply just worship, but to understand how it affects us, how creatures are affected, nocturnal creatures are affected by the light of the moon and its presence and so on, and it's affected and guided humans as well. So it's had a big impact on us, and we'll come back to that in a bit. It does have a complex structure similar to that of the Earth. It has a crust, a mantle, and a core, whereas the Earth's core is more nickel iron. The moon is more iron, not so much nickel. And so that type of, it's similar in characteristics, like it was a planet, but obviously at a much smaller scale. It orbits the Earth similarly as the Earth orbits the moon. Now, if I've got here is that its eccentricity, meaning is it elliptical or circular? It is ever so slightly elliptical. Has an eccentricity of 0.0549. So if you have an eccentricity of 0, it's a perfect circular orbit. If it's 1, well, that means it's a line or a hyperbola. So it is very close to being a perfect circle, whereas the Earth, which orbits the sun, has an eccentricity of 0.0167, something like that. It's also nearly circular, but not quite. There is a little bit of a bulge, which would, in the case of Earth, it's 93 or 96 million miles, that type of thing, from the sun. And because of this elliptical orbit, we have things like perigee and apogee, why we get supermoons when it's the closest approach to us. It does complete an orbit in 29.5 days, and that's known as the lunar month, around the Earth. And it is a rocky celestial body with much more rock and hard than rocky-like, which is a little bit different with Earth. But it has a diameter of 2,173 miles, roughly. And it rotates on its axis also. And that rotation is about 27.3 days. And which is about the time it takes to orbit the Earth, which we'll talk about as to why that leads to it faces us only on one side. It lacks a substantial atmosphere. Now, it was thought it had no atmosphere, but it actually does have an extremely thin atmosphere. Apollo 17 left behind a device called LACE, which use it to measure atmospheric gases or other gases it might find. And from what I understand, LACE, if I look here, found a variety of gases that include helium, carbon dioxide, neon, possibly ammonia, maybe even methane, but most of it was simply atoms and molecules of neon and helium, very little hydrogen, that type of thing. But if you were to say that it even has an atmosphere is giving it a little extra credit than it should get. It is extremely thin. For example, in one breath here on Earth, as I have noted here, you take in roughly, 10 to the power of 3, 6, 9, 12, 15, 10 to the power of 18 molecules of gas into your lungs and back out. That's a lot, you know. When you do it on the moon, it's going to be roughly 1 million, which sounds like a lot, but it isn't. It's actually considered to be a fairly strong vacuum. In fact, the thinness of that atmosphere is about equivalent to where the ISS is in orbit around the Earth. That's about the number of particles per cubic centimeters, or the equivalent thereof, or particles per breath, if you stepped out, and you wouldn't last very long. So it does lack any kind of a substantial atmosphere. Its gravity is about 1/6. It's smaller, not as heavy, so therefore the gravity isn't going to be as strong either. And you know, the moon is far away. I mean, it is about 1.28, 1.3 light seconds away. So at the speed of light, it'll take you that long to get there. But, you know, it's really away-ish, not that far. It's far-ish away kind of a thing when the grand scheme of things. But if you look between the Earth and the moon here, you could fit all the planets and still have a couple thousand miles left. So it's a pretty good sized distance. And I used to look at this image and go, wow, the moon is really far away. 240,000 miles is a long distance. But the problem is, as with anything on a large scale, it's something that we humans just cannot imagine. So when I look at this image here, this was taken by Osiris, a camera in 2000 on a probe, a NASA probe in 2017, and it took a look back and was doing a gravity assist maneuver around the Earth and took this image. Now, when you look at it, you're thinking, wow, that moon stays in orbit for billions and billions of years around that little marble. And it's pretty amazing when you put these things in context, or a little bit, just step back a little bit. So I'm pretty amazed by this. But let's go back to, some more fun facts about it. And it's about 25% the size of Earth, about a quarter of the size of Earth, more like 3.7. But so give you an idea here. And which in a little better context looks something like this. So it's not nearly as big as the Earth. And it is pretty gray and dusty. The dust happens to wreak havoc, according to the Apollo astronauts, with their clothing, their suits, dust getting into the lunar lander, dust getting into anything and everything, and it's not a good dust. You wouldn't want to be breathing the stuff. It can cause lung problems and other things. It's a kind of a really a dirty gray type of thing. Now, I suspect some of you have had the opportunity to see a moon rock. I did when I was about 12 years old, and haven't since. So that was like 50 years ago, not 60, 50 years ago. I saw it. God, I'm not that old, but I'm old. But it was, pretty amazing to see something from another celestial object. It is definitely a very monochromatic landscape. The only color up there is, probably a ultraviolet damaged photo now, the flag as well, and things like that. But so you can see just a little thing like the American flag suddenly puts out some eye-popping colors right there.
Fantastic.
So say that again. Oh, what was that someone said? Okay. But it is I don't know if somebody was saying it was caustic, but it is not a great dust to get inside of your ship, or to get it on you or in you in any way, shape, or form. And that's a lot of pulverizing dust. It's taken its beatings. Its rotation is in sync with its orbit around the Earth. As I said, it rotates on its axis, and about every 27.3 days, and which is about the rotational period around the Earth as well, orbital period around the Earth. And subsequently, we only see one side of the moon. And during its formation, what happened is, and the reason for that is, when it was formed, it had a molten core. The moon was molten, and as it began to solidify due to gravity, it got a permanent bulge. And this led to what's called tidal locking, and it's permanently pointed a little bit towards Earth. And therefore, it'll continue pointing. Only one side of it will be able to see it. This tidal locking is a common phenomena. It's how celestial bodies operate between each other. Also, when I talk about orbiting the Earth, there's a term called barycenter that I'm sure most of you may be familiar with, and that is that the Earth and the moon it isn't so much the moon is orbiting around the Earth, but it also has mass. So the Earth is orbiting a little bit. They're both orbiting around a center that's called the barycenter, which is about a little over 2,000 miles from the center of the Earth, about 70% of the way out from the Earth to the center, the core to the surface, is what they're both orbiting around. I think the most exaggerated example of that is Jupiter, which is so big. It orbits, and the sun orbit around that barycenter, which is beyond the surface of the sun. And so in that case, it's as if the sun is orbiting something, and that is known as the barycenter. Now, so as a result, because we only see one side, the old joke in the album and everything else, there is no dark side of the moon. And we've seen the other side of it. It looks quite a bit different. It's had a different set of impacts occurring, and the far side is just as well lit as it orbits and as it rotates around its axis as the near side. In fact, China's Chang'e 4 lander rover, and began in the new year in 2019, landed on the far side of the moon. It was a pretty exciting affair, and there it is, running around looking for a place to plant the Chinese flag, I guess, and it's been there. And obviously, American astronauts have orbited and seen the far side of the moon as well. And I remember when the Apollo missions were out there, they would go into blackout mode while they were on the far side. Wouldn't be able to receive any radio communications for a period of time. So it's a pretty exciting, it was an exciting time to watch those things. And in the spirit of things going on, not that this matters too much, but under 2 weeks ago, India's Chandrayaan 3 landed on the moon with its own rover, more towards the southern polar region, so it could go look for ice, and that occurred on August 23rd. So it's pretty exciting. But you know what? The Chinese have been there, obviously. Indians are now there. The Russians have been there, and of course, we in the United States has been there the most, and in the grandest way. In fact, if we look at moon landings, Luna 9, which was Soviet Union, was the first back in 1966. Has been there for a few times, various Luna probes and surveyors by the US, and then of course Apollo 11, 12 we'll skip 13 and 14, 15, 16, and 17, made landings with 2 astronauts on the surface, collecting things, playing golf, and doing all kinds of other mischief. But I don't think I missed any of those. But there was a time when it was just us and the Soviet Union, but that's starting to change. I believe the Emirates or somewhere, they're looking at trying to get out there in the next couple of years as well. So we have these 4 nations that have been part of landing on the moon, and it's because we put human there, unlike Mars, it's not totally a robot planet or a robot moon. So pretty exciting. But getting back to how we look at the moon, there is the illusion. The moon appears a lot larger near the horizon than when it compares to the when it's high in the sky. Now, I think we're all in agreement that that is an illusion. That's not how it is. In reality, the size is the same. In fact, even if you were to use something as simple as a tweezer, extend your arm out and measure the width of the moon when it's earlier in the night, and you can keep that exact distance on the tweezers, and then when it's heading toward the horizon, even though it looks bigger to your eyes, if you measure it, it's the same size. So it doesn't change, and that's more of a optical illusion or psychological effect. There's a couple of theories around that. Ponzo illusion, which talks about 2 identical lines appear at different lengths because of the background, as the little slow-moving GIF is showing you. Landscapes and buildings in the horizon, we already know what a building, what a landscape kind of looks like. So our mind tends to produce something that's a little bit different in size. I've kind of noticed that sometimes when I've looked at, even at San Francisco landscape off of Treasure Island, or in the Midwest, when I could see Minneapolis's IDS building off in the distance, but when you photograph it, it looks to be a bit further away versus what my eyes were telling me. There's also what's called the angular size constancy theory, which tells that our brain expects objects on the horizon to be further away and compensates. So that ultimately, it makes us think the moon is bigger than it actually is, and it's just an illusion. It's not true. And if somebody tells you otherwise, go in there and measure it, and you'll be able to see. So that kind of gives you some fun facts about what the moon is, and where how we see it, and who else has been up there, and it's not made out of cheese. It's made out of ugly dirt and dust, but it's exciting stuff. But how did it form? That's the big question that's come up for a long time. How did the moon form? Well, it's not cheese, as we know, and we're taught in various rhymes and other places. But there have been early theories that are very plausible, actually. And the first one is there's one called the capture theory. And this is the image from the animation from the European Space Agency, which suggests the moon came from wherever, another part of the galaxy, and then was gravitationally captured by Earth. Okay, that makes good sense. And it's perfectly plausible theory if you propose it, hypothesis. Then you go and test it. And well, the similarity in materials on Earth and the moon argues against that. We've gotten the moon. We've been on the moon. We've grabbed chunks of it. And we've analyzed it. They're a bit similar, and they wouldn't be if the moon came from the Orion belt somewhere, the Orion Nebula, and made its way over here after a billion years. So that's a problem. And then we look at isotopic ratios of oxygen and even other elements, and the moon and the Earth, and they're similar enough where there is a little bit more of a common origin. So the idea that we captured a completely strange celestial body doesn't seem to work here in this theory. So the next hypothesis is called fission. which George Darwin, son of Charles Darwin, proposed and claims that basically the moon just was rotating so fast, it just spit out the moon and stabilized itself after that. And that was an interesting theory, and a hypothesis, I would say, more than a theory, but it did challenge the fact that the Earth would have to be rotating really fast, far more than would be predicted. And we're looking at conservation of angular momentum and a bunch of other things, and given its mass and all that, that doesn't really seem to make sense. But it was out there, and it was definitely proposed, and so it's worth looking at. Also, the ages of the Earth and the moon would then be identical. If it came from the Earth, they'd be the same age if you examine the minerals, the rocks, but it turns out they're not. So that's a problem with this theory. So, and again, it's a scientific method, right? You propose a hypothesis, you collect the data, you test it, and you get some results, and then you move on as to, okay, does it fit the data? Do the results fit the theory? And then you develop a theory around it. So capture theory didn't work, fission theory didn't work. And then there's the co-formation theory, which says that basically they form together and in the same planetary nebula that was there around the sun, and eventually it coalesced into the Earth, and another chunk separately coalesced into the moon. Now that sounds really viable. It sounds very interesting. So maybe that's what happened. So we go on and examine some things. The distribution of materials between the Earth and moon was not consistent. We have a pretty good idea of what it would take to form the planet here and other planets that we're seeing now in exoplanets. So they're not that consistent. Earth has higher concentrations, and if it's part of the same dirt patch, rock patch, and ice and everything else, well, then they should have similar certain mineral metals in particular, even though that their crusts are very similar, but the iron composition is not the same. And the moon lacks lighter elements like the hydrogen embedded in the minerals and things like that. And so that makes us wonder if that's really the case. So, but these are three interesting and viable theories that make a lot of sense. But they really didn't work out. They were explored before they were rejected, and contrary data was generated, and then people are in agreement. So where are we left with? So the modern theory, the hypothesis, is that suggests that a Mars-sized body called Theia collided with a proto-Earth about 4.5 billion years ago. Now, this theory has been proposed since for quite a while, and I know that NASA has bought into the idea since at least 2012, probably earlier than that. The collision ejected a whole bunch of material after the collision from Theia and from the proto-Earth. Proto-Earth meaning there's no land, there's no ocean, there's nothing. It's just one big blob of molten material right now, slowly forming its harder core and things like that. But it's very hot all the way around. Theia's core merged with Earth's core, which explains why our core is bigger compared to other rocky planets on a relative scale. We can look at that for things like Mercury, Venus, Mars. The theory addresses inconsistencies found in the other moon formation theories that we just talked about. The amount of it accounts for the similar composition of the Earth and Moon's mantle, okay, beyond the crust. And was that okay? It explains the difference in iron core and in the iron core between the Earth and the Moon. And I'm glossing over these things because that's what we've really got the time for here. And it also indicates that the moon is younger than the Earth as the impact occurred after the Earth's formation. And we know that the two are a little bit different in age. So Theia was a little bit different age, and the bulk of that material is what formed the moon. And the isotopic ratios, like with oxygen in the moon's mantle, not oxygen 16, but rather oxygen 18. One of the isotopes of oxygen is different from the Earth, suggesting a different origin for the two bodies, which also lends credence to the fact that this hypothesis makes sense. And then, and that also makes sense that it evaporated some of the lighter elements because of the intense heat involved. And hydrogen would have been blown away, so would much of the helium as well. And so that explains that on the moon. So this theory, it seems to more or less, or hypothesis, more or less check all the boxes. And so as long as it holds up, it sort of remains the current hypothesis, or as we get more and more data, as we look at the isotopes, as we look at the minerals and all that, it slowly turns into a theory that we then go out and teach to everybody. But here's a NASA simulation of what happened. So there's the larger one, is the proto-Earth, and here comes Theia. So these are supercomputer simulations. Hopefully y'all can see the video. So that big blob is not the moon. That far right one is. And now we're getting near the end of it. And so there's how our theories and based on the data we have, the simulations can help lend credence to the theory as to how it would have formed, make it into a plausible view of the reality. So that's how the moon, we believe, is formed. And then after that, we have the early Earth-Moon relationship. And then initially, you know, here it's 238,000, 240,000 miles away today. But initially, the moon was only 15,000 miles from Earth. And, excuse me, this is much closer, obviously, than where we are now. And in the its early history, it began to move away at a rate of over 8 inches per year. But this also occurred over, you know, billions of years. So it had plenty of time. 8 inches adds up to a lot as the years go on. Earth's rotation was also faster. Days were only about 5 to 6 hours longer, but they both had an impact. And the moon does slow down the Earth's rotational speed. And over billions of years, tidal forces brought that to the current, roughly 24 hours per day. And we end up having to account for that every once in a while. In fact, let's see, since the 1970s, we've had to add 30 leap seconds, which just is done without us taking a holiday out of it or an extra day or anything. So, so that's the initial impact. But let's talk a little bit about some of the biggest things that it does. You know, and I know one of the biggest is seasons that I'm not going to talk about. I don't think we have the time, but tides are always very interesting. There's daily changes in sea levels, and because of Earth-Moon gravitational, and the sun is involved there too. So we have a solid crust, so it isn't going to deform a whole lot, right? But the Earth also has a liquid ocean. Over 70% of the Earth is liquid on the surface, going down for miles, and that is open to and subject to gravitational effects from the moon and the sun. Now, the moon has tidal forces that cause is twice as strong as the sun's, but they can work against each other and they can work together for stronger tides on Earth. And now, because of our rotation each day, we end up with two tides, two high tides and two low tides, two of each kind. And I'll show you what I mean by that. This always comes up is, so the gravitational force from the moon creates a high tide on the side facing the moon. And intuitively that makes sense, right? The moon's gravity, the Earth's liquid is pliable and we can pull on it, tug on it, to a certain amount, and it'll rise and fall the tides in the morning, and we see that twice a day. And there's an inertial effect or a centrifugal effect on the other side that has an opposite effect, but that also causes on the opposite sides of the Earth. So low tides occur also 90 degrees away from where the high tides are occurring in any given 24-hour period. So like I said, you've got the tide that's facing you, that's the higher tide, and on the opposite side of the Earth, there is a high tide as well. And let me show you what I mean by that. So you've got this gravitational effect on both sides, and this is what's happening. And tidal bulges due to gravity occur at this point. Now, so this is the net tide generating effect that results here. And on the opposite side of the Earth, as I said, there's less of a pull from the moon's gravitational field versus the other side. So as the Earth is rotating, that sloshing liquid can, or the centrifugal force can allow it to move more away in a straight line and therefore bulge out. And that's why you get the second high tide on the opposite side. And so as you're going around, you've got high tides, low tides. And if the sun is there, then you get larger tides. And you end up with, solar tides, or known as spring tides, king tides, like neap tides are the smaller ones. But here we've got the sun and the moon on the same side. You've got king tides there and spring tides. So hopefully this makes sense. If not, say something. And but this is how the tides work. And I found this to be fascinating, especially the fact that where just a little bit of the effect from the moon is not on the other side, and you get another bulge. And it's amazing, right? What the moon is doing. And those tides are absolutely important to Earth. The moon also has phases, as we all know, right? That's determined of the amount of sunlight that is illuminating it. And so every 29.5 orbital days. Now, mind you, I refer to things like 27.3 days to go around or 29.5 days. I'm being a little bit fast and loose with something called sidereal rotation and what's called synodic rotation. We don't have to worry about that. One, the sidereal really has to do with how the rotational time, based on how it appears with other stars in the region, as opposed to synodic time, which has to do with the moon as seen from the Earth, which is 29.5 days. But it goes through these cycles. And if anyone's interested, write me and I'll give you a better explanation of this. I remember when I got tested on it, it was a pain. But there are 8 phases of the moon, which I'm sure we're all familiar with. And, you're out there at a little family gathering and there's the moon. You can explain, is it a waxing or a waning or whichever one it is, gibbous, crescent, and so on. So, or a better way to view it is here. We have the new moon, waxing crescent, waxing gibbous, quarter moon, and waning gibbous, and so on, all the way to a full moon. So it's and obviously from an observational perspective, we want to be able to see the new moon, least amount of light pollution. Then there's eclipses, right? So now eclipses are very exciting, especially right now. This is a image of nearing totality in 2017, the great eclipse. I don't know if how many of you got a chance to go around. I went to Kansas to see this on August 21st. We actually ended up with a cloudy day and even some rain, but we got a really good shots, and it was clear enough. And when totality hit, it was shocking to see how dark it got, and automatic lights in cars turned on, headlights and all that. Pretty interesting time. But it was the first time I'd been able to see something at 99 point some odd percent. Last time was in 1979 when I was in high school. But you have solar eclipses, and where the moon comes between the Earth and the sun, blocking the sun's light. And lunar eclipses where the Earth comes between the sun and the moon, casting its shadow. And you get that redness, that blood red look as the atmosphere of the Earth's, as sunlight passes through the Earth's atmosphere, beginning to cast a shadow on the moon. And it gives you that red color, the long wavelengths that go through, whereas the short wavelengths is scattered. The sun is 400 times farther away, larger and 400 times farther away. They generally appears the same size, both of them, to us. Therefore, during a solar eclipse, the moon can cover the entire disk of the sun, and that's really lucky for us. And this alignment is not permanent, but that's the way it is right now, and will be for the next 10,000 generations at least. But another view of the what is a lunar eclipse, and so here you have it, and this is a image that both of these images I took during lunar and solar eclipses and all that. And so you also have the solar eclipse, and here sun and the moon and the Earth line up in the middle. And this is a total eclipse. Now those little on the edges, the colorful and sparkly stuff is known as Bailey's beads, discovered by an astronomer, Bailey, a British astronomer. And that has to do with the fact that the moon is not a smooth surface. It has mountains, hills, and valleys, craters, and all that. And that's sunlight going through the edges and giving us that effect. So that's called Bailey's beads. And that was my poor man's filter of the first time I ever took an eclipses photo, made with on a Canon camera.
Awanish, we have a question.
Yes.
Yes, that doesn't seem to, that picture there of the total eclipse, that doesn't look like Bailey's beads. Those are brighter prominences.
I think they've been enhanced, because where I got them, it listed it as Bailey's beads, unless they presented it wrong. I'll look up the source, but it could be enhanced, but I'll double check it.
Right.
And so these are the various phases as you go through total eclipse, partial, and so on. So lunar eclipses occur only during full moon and can last several hours. Solar eclipses only occur during new moon and are much shorter. They last at most about 7 minutes and 40 seconds. And their solars are localized events, so you got to be in its path. Whereas in a lunar eclipse, well, if it's going to be night that night, you're going to be able to see it. And so it can span across the entire continent and beyond. And just to finish that off, there's the couple of the parts. There's more to it, but the umbra is the part of the moon shadow where the sun is completely blocked, and then there's the penumbra, which is the partial eclipse occurs. So there's a lot that goes into analyzing eclipses and predicting them, but fortunately at this point we know pretty far out as to when the eclipses are going to occur. Unfortunately, we won't be able to get total eclipse forever. The moon is moving away, and the Earth's spinning on its axis about 30 times faster than the moon's orbit around the Earth. And this leads to a tidal bulge that's slightly ahead of the moon, and then gravity kicks in. To give you an idea, what that's causing it to do is that the bulge moves slightly ahead in this animation of the Earth is causing the moon to try to catch up to it, therefore speeding up. And by doing that, it's like being on a rope or at the edge of a merry-go-round. As it spins faster, you're going to be forced to move further away, and that's going to speed. And the result is the moon is moving away, and the energy associated with that. The resulting effect is that it tends to slow down the Earth's rotational speed as well. So that's where some of the energy is going or coming from. But the moon is slowly moving away from the Earth, and whereas at first it may have been 8 inches per year, it's currently drifting away at about 1.5 inches per year. And so in many hundreds of thousands, millions of years or whatever, it will not be, total solar eclipses will not occur. So, but if it does go away, you know, what if the moon was gone or never existed? The result would be that we have the Earth's tides would be only about 1/3 the size. This would affect marine ecosystems and have an impact on slowing of the Earth's rotation. So there's a lot of different effects that it would have immediately. The gravitational influences, it stabilizes our 23.5-degree axial tilt. Without it, we're going to have extreme changes in tilt, extreme climate shifts will occur on an ongoing basis. So it has a very stabilizing force for us. So it's interesting because this is the system, and that's how we evolved in that system with these conditions. And it does offer illumination at night, which can affect from, you know, old style sailors all the way to nocturnal animals. And so those would all be affected. It also picks off some of the meteors and other things that could impact us. Obviously, we haven't had a comet come around to impact with it, but there was a time in the earlier part of the solar system when it absorbed a lot of those things that could impact the Earth. So I know that I want to try to keep everything to be within 1 hour, but so getting towards the end here. So in conclusion, what I want to say is that its gravitational effects causes our tides, which is incredibly important.
Question?
Yeah.
Point of interest, annular eclipses were not discussed. Yeah, as far we can already see what happens when the moon is further away. With the annular eclipse, there's one next month, not too far away from us.
Yes, you're right. And I haven't talked about that. In fact, that was under the definitions. I removed that just for the sake of brevity. I have other slides that have all that in there, but you're right. There is one next month, and isn't there one before next April or not?
Or just those two. Just
those two, okay. The reflected sunlight illuminates the night sky. It influences species behavior. Studying is key to our understanding. It's also a stepping stone, and it's obviously had an impact on our religion, culture, mythology, calendars, and so on. And it's quickly becoming a gateway for other things, and there's even talk or hopes of putting telescopes in the dark side of the moon. we can get, and more than, and not just optical telescopes, but also radio telescopes, shielded from interference from the Earth. So there's a lot of different benefits, opportunities, potential, and of course, reasons why we are where we are with it. But there are upcoming big solar eclipses that are that we should be aware of. This is on a global from 2021 to 2040. So let's see. The line going in blue here is the 20 across the US on the eastern side is the one that's coming up. That's a big deal. So there's a lot of these occurring each year. In particular, we have some that are coming, and we had the August 2017. There's the April 2024, and then the August 12th, 2045 that are coming up. And most importantly to us, we want to look at this one, the total eclipse coming up in April 8th. Now, I've seen some of the chatter on discussions going on our group's IO. It looks like a number of people are going to be out there, have a place or a position where they can watch the totality. I think I have an opportunity to be in Dallas, which is good enough for me. And I'm going to be out there, and hopefully the weather will allow us to see what we want to see. I'm just curious. I can see a little bit of the room. Raise your hand if you're going to go and see this eclipse. There's at least a couple of hands out there. So good. I see electronically, Todd and others. It's going to be exciting. You know, when I saw the one in 2017, I said, well, I've seen it and it's not going to be that big a deal, but it was a big deal. And so if you get an opportunity to be in that band, to go see it, go see it. It's worth it. It's really worth seeing it. So anyways, this is coming up on 1 hour, and I really wanted to thank you for this opportunity.